he has many publications both in national and international peer-reviewed journals, and I'm very happy to say that he is always available for us, be it taking classes like this, or guiding us in our projects, or reviewing our progress, or whatever we call it. And despite his busy schedule, he has agreed to deliver his lecture to all today. So I invite him to proceed with further proceedings.
Thank you, Rai. Good morning to all.
Good morning, sir.
Are there any familiar faces I am looking?
Few of them. Somebody has done some dissertation works and all here.
Ali is, you are right, it goes. How many are you working with ocean color data? Rebecca from IIT?
Bombay.
IIT Bombay. Okay, then Priyanka?
Annamalai from Annamalai.
Kasan, you are from Kash? Central.
Yes,
With whom you are working?
Dr. A. Saravana Kumar.
Then nobody has worked with ocean color data.
I am from Bangalore University.
Oh, okay, fine.
Sudhakar from CSLD. Cast.
Development.
Nominations.
Right. And what is meant by working with ocean color data? Have you processed the digital data taken from any station or level 1B data or copied from any one of the sensor or processed or you are used the derived product? Who are familiar with the processing of ocean color level 1B of any sensor data?
Using CDAS software, I've done
You have done.
for Modi's and Oceanside.
You have processed it yourself. Excellent, very good. And how many of you are the biologists and how many of you are the physicists? Physics in the sense with physics background. You may not be directly physicists. How many are you biologists? Raise your hands. Rest is all physicists.
It is from environmental sciences, sir. Myself, environmental science. Yeah.
And how many of you are good on measurements of chlorophyll or identification of phytoplankton species with very low-end microscope to electron microscope to flow cytometer? How many of you familiar? Huh? What is this? All bad. You never identified the phytoplankton species. Courses on phytoplankton functional types, no? Then only you.
Sir, not marine species, but freshwater river species are identified.
Whether it's freshwater, brackish or marine water, have you ever identified, collected the phytoplankton, identified the species, characterization with small spectrophotometer to high-end flow cytometer? You are all, what is that you did?
Phytoplankton.
Phytoplankton identification using what?
Microscope.
What type of microscope?
General microscope.
Ordinary microscope. What you do after this course? You have any objective for attending this course? Because somebody has sponsored you okay. Huh? You are all young guys actually. How many of the junior research fellows here? Research students? 1, 2, 3. Good number. You are all working with projects or PhD? Yes. That means you are getting fellowship or you are doing PhD. Fine. You are all ecologists, huh? Sorry, see, okay. First, a little bit of marine optics and marine ecology. What it says, on this planet, the light directly or the life directly related to the energy supplied to the sun. That you are all familiar, no? Without sun, why? Why sun is required for life? The night time we are happily living, no? Why sun is required? Huh? They are not living without light. Antarctica 6 months there is no light. People are happily living, going and staying 6 months. Why? Huh? Why?
It's a source of energy.
Why light is required for the life? What is light?
Source of energy.
Form of energy. What it gives us to know? Energy, light gives energy fundamentally. Okay. That is having through electromagnetic spectrum, which is a function of wavelength. These are all different. Energy comes, light is nothing but energy, flow of electrons. Correct? Without light, a plant cannot do the photosynthesis. So, photosynthesis is basically ecological process for photochemistry or primary production. Correct? So, food comes from photosynthesis. Energy required human being to live. That's why light is the fundamental property or essential for planet to survive. Something is wrong with this fellow. I just read the pyramid of life starts with the absorption of a fraction of this energy by its conversion from electromagnetic to chemical energy, that is photosynthesis, and its subsequent storage into biomass, that is primary production. This chemical energy supports one way or another way the pyramid of food web that exists in the world. That is the essential of life. Okay. The study of food webs is not necessary. We will go straight away to it. The study of energy propagation to the planet is called the geophysical optics. There are two categories. One is called the meteorological optics, mostly deals with the electromagnetic radiation propagation from sun through the atmosphere, and which is called hydro-optics or hydrological optics, which we are going to deal now. That means light penetration into the water column or light interaction with any water medium. That is what is defined by the great Fresendorfer, who is the pioneer in the light penetration and light interaction with the marine ecology. Okay. Most of the solar energy striking on the earth falls into two broad bands of the electromagnetic spectrum. One is called the visible energy, that is between 400 to 700 nanometers. There are a number of names or synonyms are there, approximately between 400 to 7 nanometers. What we call it is visible light. In terms of marine ecology, we call it the photosynthetic active radiation, or of late it is called the PUR, photosynthetically utilized light or usable light. A PAR is different. In that PAR, how much is really being involved in the photosynthetic process is called the PUR4. That is what critically accounted for the marine ecologists as on today. The second one is hydro-optics. Then most of the solar energy striking the earth falls into two broad. Visible, and the rest is the 700 to 1000 micrometers, or 100 micrometers. So broadly you have a visible light, then you have infrared light. Even though infrared light is also very critical for remote sensing, but Today we are mostly dealing with visible light because that is where the marine optics is. The study of ocean optics is primarily concerned with the propagation of visible light or the propagation of visible energy or visible light into the water column. Okay? There should be a light that has to be propagated into the water column. In terms of remote sensing, my colleague Anis will teach you, light has to penetrate or propagate into the aquatic media, interact with the media, and it has to backscatter from water column to the atmosphere and reaching to the sensor. That is what the remote sensing will do. We are interested today basically how the light is being penetrated into the oceanic water column or aquatic water column, because you may be working on lakes, reservoirs and estuary, and how it is interacting with the respective aquatic media is interesting. Photosynthesis is driven by energy within the visible light spectrum, which has sufficient energy for photon to introduce the photochemistry. Be careful, you have a term called photon, energy for photon, and another term called photochemistry. So light penetrates through light or sunlight, radiation from the sun or light from the sun propagates through electromagnetic radiation, which is called a photon. Photon is a small element of energy carrier. Okay, what it is the relation we will see. Phytoplankton accumulations impact the color and clarity of the water column. There is a direct link between the ocean optics and ocean ecology. What it says, phytoplankton accumulations, a single or group of phytoplankton or patch of the phytoplankton impact the ocean color and the clarity of the water column. That means there is a direct link with the ocean optics and the marine ecology. A growth of phytoplankton and accumulations, the total light absorption increases, reducing the total light flux to deeper levels. A growth of phytoplankton or patches of the phytoplankton absorbs the light. So in that process what happens? Reduced light or decreased light only penetrates into the water column for the nest level. So the most of the light is absorbed by the phytoplankton process. Very, very minimum light is available to the nest levels. If they survive, then what it means? The light flux to the deeper levels is reduced. That means when light propagating to the water column, it does two things. Okay, an incident light on the sea surface or any water media has to be penetrated, interact with the water column and backscatter. That is different. Remote sensing will take care of backscatter. While penetrating, the light penetration into the natural water increases exponentially with the depth and decreases with the increasing of wavelength. Two things happen. When light penetrates into the water column, exponentially decreases in terms of e to the power of some term, exponentially decreases with depth and also decreases with wavelength. So it is a function of depth, that is Z, and also function of lambda, wavelength. So the penetration of light is a function of Z or D, lambda, and also in 3 dimensions is a function of time. Why? Because sun's light is a function of time. You have a morning, very minimum light starting, and you have a maximum light during about 1:30, tending to which is a sinusoidal curve. So the penetration of light is a function of Z or D, wavelength, and T. If you really want to classify or parameterize or account or at any given point of time what is the light available at a given certain depth, you have to account all these at that depth, what is the wavelength structure, what is the depth, what is the media available, and also the time. That's what it says. The photochemical conversion of visible energy to biomass, be careful, photochemical conversion of visible energy to biomass is a negative biological feedback. photoconversion, photochemical conversion. You are all familiar with photosynthesis. Conversion of visible energy to biomass is a negative biological feedback, creating instabilities for the future growth rate of phytoplankton. So that is the critical of the photosynthetic rate processes. Ocean optics and physical process are linked to the radiative heating of solar radiation absorbed by the ocean water mixture, that is pure water plus particulate and dissolved matter. The physical processes are linked to the radiative heating of solar radiation absorbed by the ocean water mixture. When the light is penetrating in the presence of phytoplankton, okay, what is the job of phytoplankton? Photosynthesis, but it absorbs radiation selectively. That is called the selective absorption of light by a given phytoplankton species or the group of species. Not only that, it also fluoresces. The in vivo, in situ, in vivo. In situ means at that depth, in vivo at that particular time, it absorbs the light and also it fluoresces the light at a given wavelength. But this absorption is a selective absorption by the different species at a different wavelength. That means it's a function of wavelength, also function of the type of species, which the subject today is the phytoplankton functional type. What is that phytoplankton type and what is its function with respect to the wavelength is the matter of it. The solar radiation penetrating the atmosphere has a spectral distribution. Each wavelength contains a varying fraction of the total downwelling energy. That's what photon energy. Distribution of radiative heating in the water column. Distribution of radiative heating in the water column is dependent on both the spectra of the incoming light and the spectrum of the optical properties of the water column present in the. Hello? Sir, నేను క్లాస్లో ఉన్నాను. ఆఫ్టర్ 11:30 I will call you. Okay. See carefully. The distribution of radiative heating in the water column is dependent on both spectra of the light available or incoming irradiance and spectrum of optical properties of the water column present there. So there are two types. One is the radiative heating or the light available at that particular depth is a function of wavelength, spectral distribution, what we call it, and also the optical properties of the water medium. What are the fundamental optical properties of the water? Anybody have any idea?
Absorption.
Scattering.
Scattering.
You told you are measuring, no? Chlorophyll you might have measured anything. Now, what do you do with the chlorophyll measurement? Anybody who is have a clarity, how you measure the chlorophyll, what is the process involved, and how you get that result? Okay, you collect the water sample, add some chemical reagent, then you bring it to lab or on the desk. What you will do?
Filter.
We will soak in some other media. We will soak that filter powder in some other media.
Okay,
And we will extract that filtrate.
okay.
And we will measure them by spectrophotometer.
Measure with what you measure?
Or
Okay,
and
what,
absorption.
what you measure with the
We'll measure
Absorption light of the chlorophyll.
absorption at what length?
They'll absorb at 447 or 667 nanometers.
Only that much? What is your chlorophyll estimation equation says finally? How do you estimate the chlorophyll? Chlorophyll is equal to some equation in the depth of the.
Depth of the water column and filter water.
Okay.
And factor. Factor in.
What is the factor?
The factor will get by calibration.
Oh, you are not estimating the chlorophyll using any spectrophotometer. You can estimate with the simple spectrophotometer, powerful UV spectrophotometer, then fluorometer, then other instrument that is different. What is that wavelength you are passing through that water media? Small pipette or what do you call that one? Cuvette. That is exposed to a light at what wavelength or the spectrum of the wavelength? At a particular wavelength you are exposing, what is that wavelength?
Visible.
440. So what is the relation between the 443 and the so-called
Lambda maxima.
No, that's okay. What 443 does? Why 443 only? When you have a light from 400 to 700 nanometer, I can expose at 400, 443, 500, 550, 600, 700. Na? Why the light you are exposing for estimation of chlorophyll at
Because
443?
chlorophyll has a lambda maxima at 440 nanometers. Light absorption capacity is high at that particular level.
Very good. That means chlorophyll or the phytoplankton has a characteristic of absorption of light at 443. That is a presumption. What I told, phytoplankton are having a selective absorption peaks. A selective absorption peak, not one. What you are using is 443. Okay, but people uses at 490. People uses 500, 550, 530, correct? And people estimates the chlorophyll by using the fluorometer with fluorescent processes or fluorescency processes, which in vivo fluorescence at 683. You can absorb, you can fluorescent. Either you can measure by absorption technique or using the fluorescency techniques, you can estimate the chlorophyll. When you use the fluorescence techniques, when you use the absorption techniques, we will see that. The solar rate or the solar energy penetrates the ocean surface. Vast majority, more than 99% infrared is absorbed. 99% or greater than 99% of the infrared. Infrared means beyond
700 to 0.1 micrometer.
is absorbed within the first 1 to 1.5 meters of the water column. So that means what? So water column is 100% opaque for the infrared light. There is two advantages. Beyond 700 nanometer, light is not penetrating into the water column. If at all, if it penetrates only one of the first 1 meter level, that principle is actually being used for the remotions. Okay, keep it. Tomorrow Anish will tell that. Huh? In the visible part of the spectrum, the depth of penetration varies dramatically with optical that we have already discussed. The radiation absorbed in the upper ocean is converted to heat, and its depth distribution is determined by the transmission function that is called the tree or the transmission coefficient, or in the atmosphere also we use that equation T. That means transmission of the light or the loss of energy, which we call it the total attenuation coefficient, which is a function of lambda and z. Okay, that means what we have a light at surface 100 units. What is the light at 1 meter, 5 meters, 10 meters, 30 meters? That depends upon the total transmittancy coefficient or the transmittancy of the water column, which is function of again lambda and z. ED 0 minus, suddenly ED has come, that is called the energy. In the marine optics, light is measured spectrally in terms of remote sensing. What we call it as a radian, downwelling, radian upwelling. Okay. So you have a downwelling irradiance and upwelling irradiance. Same thing with upwelling irradiance also, and a term called the reflectance. I will read one by one. T is not routinely measured, but various parameterizations are used to account for the expected depth dependency of T for discrete wavelength. Be careful. T is not possible to measure unless you have a transmissometer, which is very difficult, people costly, and is very cumbersome also. But T can be parameterized or T can be estimated by using the other parameter, okay, for the expected depth dependency of T with the wavelength. For most water types, variability in T is primarily due to phytoplankton pigment. This starts with marine ecology. T basically depends upon the availability of the phytoplankton and its pigments and its other pigment associations at that particular depth. The most ubiquitous of which is chlorophyll A, which is primarily present in most of the phytoplankton species, and this chlorophyll concentration be used as the basis for T parameterization. What it means, I cannot measure the T directly, but T has a direct relation with the biomass present, that is chlorophyll present, which is synonymous to the phytoplankton. Some phytoplanktons may not be having, but most of the phytoplanktons are having chlorophyll A is one of the primary. By knowing the chlorophyll, you can estimate the transmittancy of the light. Okay. Otherwise, if you know the light, you can characterize, but measurements of light is difficult. All biologists or ecologists are familiar with measuring the chlorophyll A. From that chlorophyll, inversely you can estimate the transmittancy of the light, which is function of, transmittancy is a function of what? Absorption and scattering, which we call it as a total attenuation coefficient. At this point, just see here, some point, underwater light field. You have light speed which is having about 3 to 10 to the meters per second in a vacuum. In water, what is the light speed? Is the same or different? Huh? Approximately 2.88 into 10 to the power 8. Okay. Remember, 2.8 into 10 to the power of 8 and 3 is a lot of difference. Even though it looks like 3 and 2.88, 2.88 difference of 0.12 multiplied by 10 to the power of 8. Attenuation. These are the terms. It comes from the marine optics. In water, light intensity decreases exponentially with the drips from the surface or from the source that you are corner. Light decreases exponentially with the depth. Okay. Then attenuation. Attenuation. What is attenuation? Exponential loss of intensity. That is absorption of scattering. By penetrating, energy is lost. That is called attenuation. If you measure attenuation coefficient for unit wavelength, which is a function of absorption and scattering, add absorption coefficient or absorption and scattering, you will get the attenuation. Absorption is what? Conversion of electromagnetic radiation to heat or chemical energy, which is called the during the photosynthetic process. So who are those absorbers? Phytoplankton. Then only phytoplankton.
Water, organic matter.
Yeah, who are those absorbers? Phytoplankton. Inorganic and organic particulate matter in suspension. Organic and inorganic material in suspension, other than algae. Dissolved organic material. You heard the name of the.
Sedum, color dissolved
Yeah.
matter.
You are only telling. Pseudo is what? Colored, dissolved organic matter. It should be a dissolved one, and it should have some color. Color depends upon what type of organic material is dissolved by decomposition. Okay, that is called generally we call it as a yellow substance. Because mostly it is a absorption yellow. It is also called the pelvic substances, also called the gelbstock, also called the degraded material, which is called from the carboxyl group. There should be a plant material, it should be decomposed, it should become converted into the carboxyl group. Then it should be dissolved into water column. That is called an organic matter dissolved into the water column, which creates some color other than the existing pure water or the oceanic water. That term is called the sea zone. Colored dissolved organic matter or yellow substance or gelbstock or carboxyl, all are synonymous. Now, what is the sedum characteristic? Optically in the water, because we not only marine optics. Absorption is having a selective, phytoplankton or chlorophyll is having a selective absorption. Selective absorption peaks at different wavelengths. Whereas this fellow, sedum, absorption increases with the decrease of light. Absorption only increases with the decrease of light fundamentally. But we cannot accommodate because the light below the 400 nanometer is dominated by the scattering rather than the absorption. In absence of scattering, in the water column, if you want to measure the CO, a simple absorption measured at 400 nanometers or 300 nanometers, 350 nanometers or selectively between 350 to 400 nanometers, if you develop a slope of the curve, that gives the strength of the absorption by the colored dissolved organic matter. Okay? That means if I want to estimate the colored dissolved organic matter using a spectrophotoskope in the field or in lab, I should pause the light at 400 or 380 nanometer instead of 440 for the close. Because that is a selective absorption, is a continuous absorption, increases with the decrease of wavelength, but because light is having so much scattering in the lower wavelength, especially in the beginning of the blue end and the middle of the blue spectrum of the blue band, you cannot estimate. That's why water looks like blue, because most of the blue light is scattered below the 400 nanometer. Then, water itself. Okay? A water, a fundamental water, H2O, pure water, is having its own fundamental optical properties called absorption, scattering, or attenuation, which is called the inherent properties of the water itself. If the material is present, those coefficient changes, but if in the absence of any material, in pure water itself is having its absorption as well as the scattering. That means in the pure water, light decreases with exponentially with the decrease of depth and also decreases with increasing of wavelength. Now, A and B is known as a system. That's what the total bioorganic material present into this one. Then what is scattering? Change of direction of electromagnetic radiation due to the multiple reflections. That is called scattering. Most of this scattering is in the forward direction. When the light penetrates, there is a multiple reflection. That reflections also the forward scattering. That means a photon penetrating into the water column from 1 meter to 2 meter is in the forward direction is maximum. A very small amount between 0.1 to 2% only backscattered. In remote sensing terms, in biological terms, what we are interested in is the backscattering energy. Light penetrate and also backscatter, but this forward scattering is called is very high. Only very small amount is available for backscattering. But in other words, being ecologist, you think of light is penetrating and you are losing the light, decreasing with the depth, and slowly you may not get the light beyond the 14 depth. 14 depth is nothing but the available of energy for 1 meter, 1% of the light from the surface, where allows the photosynthesis process. That is called photic depth, photon available at depth for photosynthesis. That is called photic depth. Now, what is photic zone? Illuminated zone, also called. Intensity of light is sufficient for photosynthesis primary production, leads to the net growth of phytoplankton. That is called the photic depth. These are the terms regularly you will use in the marine ecology. Then there is another term called the Secchi depth. Most of the ecologists measure the light crudely on his optical depth, photic depth. How much photic depth? How do you know? There is a small disc of 20 to 30 centimeters, painted as a white or white, paint white, block white, light is painted. And while you wiring that instrument, wherever that Secchi depth is disappeared or not able to see, up to that depth is called the photic depth. Now you got, no? That is called the depth. it is not a very crude instrument. Instrument likes very crude, but it speaks a lot for the marine ecology. If you really understand the light and its water column interaction and the principles of light penetration, this Secchi depth for a marine ecologist speaks a lot, and till today that is quite good enough to explain the photosynthetic and phytoplankton species present in the water. You need not have a big radiometers like what Anis is having, but fundamentally you should have a Secchi depth and you should know what is that Secchi depth, how depth, what is that. Number one. Number two, the light emerging from the water column is directly proportional to the, in general, 1/3 of the Secchi depth. What we do is, photic depth where 1% of the light from the surface or where the photochemical actions are present to do the photosynthesis, that much energy is sufficient is called photic depth. Otherwise, if I want to measure the light backscattered from the water column, that principally or generally 1/3 of the photic depth or 1/3 of the Secchi depth column from where the light is backscattered. That means I want to measure the light coming from this water column. I expect the water leaving radiance or the so-called backscattered light. First what I do, I will measure the Secchi depth. Say for example it is about 30 meters. So 1/3, that means what I am measuring the light, I expected that light is coming from the 10 meters, 1/3 of the depth. So that is what remote sensing has been used. Now Secchi depth check, this is what I told. Depth at which the disk disappears when lowered to the water column in horizontally. You should not have a slide or you should not deviate from your direction of horizontal axis. So that is called Z dash. Is a function of F by C plus K. What is F? F is the factor depends on the reflectivity of the disk. Suppose if the disk is completely blocked, you cannot see complete weight. It should have very clarity. It also depends upon the material which you have used for the disk. So that is a factor depends upon the reflectivity of the disk and the background of the observer and the perception of the water column. What it means? If the Secchi is, what is the background of the water column means? When you lower the Secchi, what type of bottom is present there and what type of water? That is the background is. Suppose you deploy a Secchi disk in your own well, a deep well, it goes up to 50-60 meters. Correct? But if you go to the open ocean, it is about also 60 to 70 meters. Then you go to the coastal water, it disappears within 5 to 10 meters. That not only depends upon the water column characteristics, it depends upon the background or the bottom of the water column. Suppose your bottom is a sandy, clean, very clean sandy bottom, then your resistance is very high, it goes up to the bottom. If your bottom is dominated by say muddy or some minerals, so that's what he said. It depends upon the disk reflectance, also backward, and the observer's penetration. If you have a very clean eyes with this one, also depends upon how clearly you are using, parallel curves and all that one. So this is what it means. That's why I told Secchi disk is not a simple, even though it's like imprint, or marine ecology, it speaks a lot. Second one is, what is C? That is called the attenuation of light. Then K is the diffusive attenuation coefficient for non-directional light, that is called the extinction coefficient. So the Secchi disk speaks of the factor of the reflectance of the disk divided by the attenuation of light plus diffusive attenuation coefficient. That means a marine ecologist with a simple Secchi depth or Secchi disk properties with spatially, you can define the attenuation of light and also you can calculate the diffusive attenuation coefficient. See, a small instrument in the ocean gives the total attenuation and also the diffusive attenuation coefficient and in any given direction. Now, it is about 8.7 F. The F factor is about 8.7 in clear water and about 6 in turbid water. If your disc is clean, the F factor generally varies from 6 to 8.7, depends upon the depth of the water column. Then diffusion attenuation coefficient versus the Secchi. K is called the diffusion attenuation coefficient. That means diffusion of light for a given unit of length. That is called the diffusion coefficient. Units are lost for meter or minus meter. K into Z, which is a constant. K is equal to 1.5 in general. So then you can find out the ZS. The attenuation coefficient is V is equal to 0.7 into ZS is very general. That means if you know the ZS, if you can calculate the V, if you know the V, you can calculate the ZS. That means V by 0.7 gives the ZS. The depth of the photic zone, ZE, previously the Secchi is there. Based on that ZE, photic zone depth is equal to 3 of ZS. This is what I told. Or ZE is equal to 3 by 0.7. Even though you can see the line up to 30-40 meters of your Secchi, but the depth of the photic zone is approximately 1/3 of the depth of this one. Then you have a beam attenuation coefficient, then you have infrared merging, this is what for. Now come to our. These are the terms you remember. And is up to 11, huh?
Yeah. Sir?
This spectrum of light I am skipping. Photon of energy I am coming. Refractive of index of water. This you remember. Refractive index of water is 1.33 in natural water. Varies with the temperature, salinity and wavelength. And the refractive index of air is 1.00028, assumed as a 1. Why? Because the light is penetrating from atmospheric column through vacuum, through atmosphere, from atmosphere to the water column. When you measure the light emerging from the water media to the atmosphere where it changes. So C in water is equal to approximately 2.25 to 10 to the power of 8 meters per second. Okay? These are all definitions. I am not sure how good. Okay. You read terms called radiative flux. That is the rate of flux of radiant energy in watts or joule seconds per in quanta. Generally, you express marine ecologists always express quanta of light. Okay. But the quanta conversion to the watts or joules is critical. Generally, you measure in any photometer for marine ecology is called quanta or luminescence. You know what is the luminescence of the bulb. Then finally you convert it into the what type of wattage. You have to have 15 package. But generally we measure, marine ecologists measure in terms of quanta. The direct conversion from quanta to watts is a little bit conversion process, but there is a constants are available. Then the radiative intensity. Flux for unit solid angle, flux for unit solid angle in a specified pi direction. An infinitesimally cone is given in direction on the element of a solid angle. What it says is, if I measure the light available here, or the incoming irradiance, or the total light between 4 and 2, what is R available on the surface, is called the irradiance or E0, that is radiant. If I measure the flux, that is radiant. Flux is the time, that is radiant flux. The radiant intensity, if I want to measure, I can measure total or I can measure for a small angle, like your camera. Okay? All the people are having cell, you have camera. You focus on an object. What it means? Your focal length is defined very small, focus only to the small element of your target. If camera is wider, what is that? You are allowing more light from the target, allowing to come. If I allow it 25 degrees, 180 degrees at least, what will happen? Whatever the light falling on the surface I measure. That means what? if I measure, what you measure for a small angle, infinitesimal small angle, is called the radiance. Why? Because radiant flux measuring in a small angle. If I integrate over the 2 pi angle, I will get the irradiance. Okay? This remote sensing is measured the radiance. Box scattered radiance, because it is emerging from the water column, passing to the atmosphere, reaching the sensor in a given small angle, or the cone of the angle, or the cosine of the angle. That is what the sensor measures. But the energy falling from the so-called sun, great sun, on the surface is called the irradiance, or ED at 0 minus. That means 0 minus, just above the sea surface is called ED. Okay, just below the water column, very critical to define, is called ED minus. Means at the you have a water column, very thin. What measure is ED? Just below the water column, 1 meter or 50 cm is called the ED minus. If you measure in the atmosphere, ED plus. Okay. Then I, the intensity is equal d pi, means by dW for a unit area. Then watts are quantum for steradian. Then radiance L is equal to radiant flux for a unit solid angle for unit area of a plane. You please remember the difference between the radiance and irradiance. Radiance is what? L, defined as L. Okay. Radiant flux, same flux for unit solid angle for unit area of a plane. You can measure in 3-dimensional plane because sensor is in the 3rd dimension. Or you can measure here itself. That means radiant flux for unit solid angle, always remember, which is defined as a steradian. So L theta pi is equal to d square of pi into dA of cos theta dW. That is called a small element, small area, that's what the area of plane. dA is a small area, cos, cosine of in the direction of the dW is called the L, which is a function of theta and pi. That means radiant, irradiance is only a function of zenith angle, whereas, irradiance is a function of only zenith angle, whereas radiance is a function of zenith as well as azimuth angle, both. Now irradiance E is equal, once you measure L or once you measure E is equal simply d pi by dA, whereas L is equal d pi d square pi by dA into cos theta. Okay, whereas in this case simply d pi means radiant flux for unit area. D is nothing but the difference, radiant flux for difference area by a small unit of area is the point of source watts per meter square. That is again defined as the Dilbert irradiance and upwelling irradiance or upwelled irradiance. Radiance in the given direction is defined by theta and pi, that is zenith as well as the azimuth angles. The projected area of the element is small ds, a small area into cos theta. Corresponding to angle is called d omega. The radiant flux on the element of the surface within the solid angle of the d omega is L theta pi ds into cos theta into d omega. That is what the final definition for the irradiance. Okay. If you want to measure the irradiance, this is the definition for the irradiance. If you want to measure the total irradiance at that point, simply integrate from 0 to 2 pi angle of L into d theta into ds into cos theta d omega. That's why I told earlier mathematics are marine ecology I. So I skip all this one. How to measure the ED, EW. Okay, now you just see the penetration of light only, we'll discuss. I, light at a given depth is equal I0, light at surface multiplied by e to the power of minus kz. Why e? We fundamentally decided that light decreases exponentially with depth. That means if I want to measure the light at 5 meters depth, I should know its surface, that is I0, multiplied by e into minus kz. Z is no, at because I am measuring at 5 meters. Your IZ is I5. So I5 is equal I naught means the light at surface multiplied by E to the power K into Z. That means Z is 5. Now what is unknown term? Unknown term is K. Correct? Correct. No? That is called the diffusive attenuation coefficient. For non-spectral uniform depth. What it means? I am just measuring a surface. I am only measuring at 5 meters or 10 meters. But the light penetration exponentially decreases with the depth, is not uniform. Precisely what I have to do? I have to measure at possible depths. That means 0.5 meters, 1 meters, 1.5, 2, 3, 4, 5, like this, so on. Then integrate all these K's, then I will get a K.
Integrated.
But practical purpose, which I am not in a position or I am not in a position to parameterize that, I am simply measuring at surface with a photometer. I lower the photometer at 10 meters depth. I simply calculate what is the light, the loss of light from surface to the 10 meters is simply used because I know the light at surface 10 meters. Iz is known, I0 is known, Z is known. If I take the natural log, I get the diffusive attenuation coefficient for that water column, assuming uniform depth and non-spectral. What is non-spectral? Total light. I have not parameterized light at 400 or 450 or 500 or 550. The total visible light of the so-called photosynthetic active radiation of R, I at different depth, and D for that part. K for that part. Diffusive attenuation coefficient for the total light for a uniform depth. Then I will introduce one term called the Z is equal I0 into e to the 4 integral from 0 to Z, kz phi and dz phi. What it means? As I told you, I will integrate with all the possible depths because it is exponentially decreasing. If it is linear, I would not have any problem. So exponentially decreasing, I measure at all possible depths, whatever physically possible for you, maybe within 50 centimeters or 0.5 meters. Then integrate up to that. That means what? Non-spectral but non-uniform depth. First one is uniform, second one is the non-uniform depth. But still it is non-spectral, total light. Now, I z lambda. I is a function of z and also function of lambda is equal to I0 e to the power minus 0 to z, same term, kz phi and a function of lambda. If it is 400 nanometers, I will keep 400 nanometers. If it is 500, I will keep. And dz phi. What I am introduced? I have a radiometer which Anis is having, which measures the light from 400 to 750 nanometer. For every nanometer or selective nanometer that I introduced here, I will get the light spectral light distribution for that depth for that point of time. You got the point, no? At certain depth, I get the entire electromagnetic radiation between 400, so the spectral distribution of light for the defined wavelength of what radiometer is having specification, whether it is a 2 nanometers, 5 nanometers, or a band of 5, 10 bandwidths of every 400, 410, 420, 450, so on and so on. But his radiometer is capable of 2 nanometers, no? 1. Okay, 1 nanometer. That means your Iz of lambda, which is for every 1 nanometer, from 400 to 700 nanometer, you will get the entire electromagnetic spectrum for that depth or for that given depth using the underwater radiometer. If I simply want to use, I use the photometer, which is between 400 to 700 uniform. That is the final term. Spectral, non-uniform depth. Non-spectral means total. I am going to know spectral distribution of the light with spectral distribution of the light with every depth or every meter. That is the final term. Now what is the mean? Now, if I have this underwater radiometer which is given by the Enquisani is Iz, lambda I remove, integral between the 400 to 700, Again I naught lambda e to the power of minus kz prime lambda dz prime. Because I measured every nanometer and simply integrating over 400. This is the best or the most appropriate method because I know the light for every nanometer. I cannot parameterize when I have a simple light from 400 sound. I can always see. I can parameterize having all your characteristics. Okay, then I can say the mean characteristic. By knowing the mean, I cannot characterize what is his parameter. That means measure all possible depth, measure all possible factors and integration. That is mathematical. Now, K, the mean diffusive attenuation coefficient for a uniform depth is equal to di, difference of I at different depth, which is a function of z by dz in mathematical way. If somebody asks what is the total diffusion coefficient for the given depth of 10 meter, simply what I do, I will measure surface, I will measure 10 meter, surface minus 10 meter by 10 meter, because that is 10 meter. Okay, that is called the mean diffusive attenuation coefficient for a uniform depth. The same thing for K lambda introduced for every wavelength. Now, K lambda diffusive attenuation coefficient for a given wavelength is equal Kw lambda plus Kb, which is a function of biomass and wavelength. This is what fundamentally we learn. What is that? A pure water is having its own absorption and attenuation coefficient or the attenuation coefficient, or that is function of diffusive attenuation coefficient because there is no absorption coefficient, because there is no material present in the pure water. In this water, there is presumably there is no material, correct? So whatever the light is because of the diffusion of light. So that one, this one, plus the K created by the biomass. Fundamentally, we learned in ecology, loss of light in the water media is a function of constituency of the column directly proportional to the biomass, chlorophyll, which is having a link with the phytoplankton. Correct? Now, the K in oceanic water column is defined as a pure water K, which is having a tables measured by number of marine optics, physicists or biologists, that is called present doctor or Baker and Smith, so many people are measured. For every 1 nanometer, K lambda is known, then Kb has to be measured. How I measure Kb? We learn by knowing the biomass, whatever the loss light is absorbed because of the biomass, that you account, then you will get the total. If I know the total K in the field minus the pure water, I will get the light diffusive attenuation coefficient for the material present. Now, what a marine biologist or ecologist has to define, what is the so-called material present there? First, one by one. What that we thought of? Phytoplankton, organic and inorganic material, suspended sediment, pseudo, and so on and so forth. Now, virus, bacteria, leave all that one. Now, one by one, I had measured the diffusive attenuation coefficient very easily using the photometer or so-called underwater radiometer. Now, I have to define what is the role of this K or how the material is acted or created or parameterized in this K. K is a function of phytoplankton plus organic and inorganic material present plus suspended sediment plus pseudo. Now, you are the right people to decide what is dominant in that K. If I measure K in the pure aquatic water, it is purely absorption, assuming that water column is deprived of or devoid of pseudo and suspended sediment. Correct? I have an absorption from the total phytoplankton or detritus of the phytoplankton, a small scattering. See, most of what is that is the dead phytoplankton, which their skull or the peripherals is dominated by calcareous material. But still some life is there, that's why it absorbs. That creates an absorption, also scattering. Correct? So if my area is purely dominant by the chlorophyll, avoiding all that, what I will say is the purely absorption dominant type of water. Where it happened? Tell, where it happened? You don't have only absorption dominant water?
Open oceans.
What is deep oceanic water say?
Open oceans.
I will go 2000 meters deep from away from this coast. What it says? It is only absorption. Why? Other than natural scattering and natural absorption. That is known from the lab. That I will add it. Okay, whatever I measure minus the pure water, I will get that one. What is that one? Whatever the chlorophyll present in the open oceanic waters at that distance from the coast is purely dominated by the phytoplankton or inversely directly proportional to the biomass or directly proportional to the chlorophyll. Correct? That is called the case of water. Now you have to say your water type is absorption or absorption plus scattering or absorption plus scattering from some other scattering or absorption by the sedum. So this you have to characterize yourself. If the area is purely dominated by absorption, that is where I am very happy because absorption is directly proportional to the presence of the chlorophyll. If I measure the chlorophyll, I can estimate the absorption coefficient. If I measure the absorption coefficient without the measuring the chlorophyll, I can directly attribute it. This absorption is directly proportional to the present rise of the so-called chlorophyll. But to come to the nearer the coast, where we call it as complex coastal waters, is very critical. Why? Because your chlorophyll is more, not only more, variability is more. One is more, second one is variability is more. That means you may be having 0.1 or 0.2, you may be having 5 milligrams. Correct? Chlorophyll is milligram per meter cube or microgram per liter, whatever the units use. What is the expected or general chlorophyll in the open ocean water?
0.3 less than 0.5.
0.2 itself is very high, maybe 0.1 to 0.2 maximum. But come to the coast,
It's up to, based on the season, maybe 3 microgram per liter.
3.
It's vary from
Sometimes 5 also.
5 also.
Please remember the value between 0.1 and 3. How many times higher?
More than 100.
How many times higher?
More than
300 times higher, not 10 times.
300.
That's why be a good ecologist is very clear, very cautious and careful about 0.01 chlorophyll. Okay, the fellows who doesn't know much about the biology and ecology, they can speak anything. The chlorophyll increase from 0.1 to 0.2 speaks a lot. Especially from 0.1 to 3 in the coast, it speaks entirely different. Correct? Because where is 0.1 multiplied by 10 is 1. Multiplied by 13 is 3. Okay, 2 orders. And if it all 0.0, and sometimes it may be 0.5 also. That means finally the chlorophyll is varying from 0.01, which is very difficult to measure, but 0.05, 0.01, correct? And 1 and 10. How many orders? 0.0, 0.00, 0.01, 0.1, 10. Forget about 180. That means there is 3 orders, 1000 times. 10 into 10 into 10. 3 orders plays a critical role, this chlorophyll in the coastal water. Why this chlorophyll only converts into the photosynthesis, correct? Then primary productivity. When you go into that one, you will get the primary product. I will skip this. This is over. Oh, okay. Just for 10 minutes we spend. Unusuality. Color of the ocean is blue. Why? Scattering is mostly blue. And also in the lower wavelength below the blue band. The changes of water color is because of what? That 5 parameters are precisely phytoplankton or inorganic organic matter. Leave it in zero. Hello? Phytoplankton or inorganic organic material. If you remove the first one, only phytoplankton, that's where the whole conversion of the case from the water. If you come to the fourth, inorganic material, inorganic material means suspended mineral particle. Organic material means the detritus material, plus pseudo, plus bottom reflectance all comes. One by one you have to add. Okay, that's why green. If it is only phytoplankton, I am safe and it is easy to measure, estimate. Once the light is incident, it is absorbed in the water column, it is transmitted to the lower depth and reflected back. In remote sensing, what is interested is the component which is reflected back. Okay. Now, this is the story of the optic. What it shows? Sun, there is a sensor. Simply sun is there. Spectral irradiance on the top of the water column. While penetrating the light, that is called a downwelling diffuse or downwelling irradiance. Because photo. It is interacting, it is scattered, and it is spectral upwelling. This is spectral irradiance, this is spectral upwelling. Why? I am measuring the emerged light in a small cosine angle. That's why if I integrate that over the length, whatever the energy is coming in. But my sensors cannot measure. Sensor is nothing but a small camera. Like whatever the camera you have your sample, there is a camera with a spectral band, defined band. I am measuring in a small angle of that light coming in that spectral band is called this ocean color sensor. That's all. You will teach you which color is better or not. Then is come to the complete oceanic water. You have an absorption coefficient. You have a backscattering coefficient. Sun is, light is coming from the sun. Forget about the sensor timing. What is the, you have a pseudo, you have a pure water, you have a phytoplankton, you have a other inorganic component, and the non-photosynthetic phytoplankton. This what, I don't think more than anything is present in the water column other than optically. Nutrients and all that, the reaction with optics is very, very minimal. So now, what is absorption? Pseudo absorption. If pseudo is devoid, then what? Absorption is only for pure water, which is known. Then absorption by the so-called phytoplankton, correct? In the absence of inorganic material, then my absorption coefficient is purely dominated by the phytoplankton, and the light emerged from that water column after the absorption is reduced light. No? You have 1000 units in the extraterrestrial at the top of the atmosphere. From there, light water transparency, atmospheric transparency absorbs and scatters the light. A very small light is only penetrated
into the water.
Emerges or incident from sun, top of the atmosphere, multiplied by the transparency of the atmosphere, like loss of light in the atmosphere. That much is only incident on the water column, on the water surface. That light has to penetrate into the water column, while penetration natural law because of its pure water characteristic, then absorbed by the chlorophyll. What is left? Very small amount is left, which is backscattered from the water column, passing to the atmosphere, then reached by the so-called sensor. At top of the atmosphere, light at the sea surface, penetrated, absorbed or scattered, then backscattered. Please remember, backscattered, not for backscattered or reflected, a very small quantity of light. Again, this fellow has to pass through the atmosphere, reach the sensor. That is what you measure. So, looks very easy, but if you apply all these corrections, very complicated. Somebody told us, reader, that fellow explains all these complications for us. Now, if you take both absorption plus backscattering, what is backscattering? Pure water. Luckily, there is no backscattering from zero. we discussed, only absorption that too increases with the decreasing of wavelength. Whereas phytoplankton are selective absorption. Then phytoplankton, then inorganic matters, and non-photosynthetic. So wherever the backscattering is present, by any material, process is complicated. In addition to that, wherever the sedum or the dissolved organic material is present, still is three process is complicated. Absorption plus backscattering plus sedum characteristic. So these work finally. Water, phytoplankton, organic, inorganic materials, suspended particles, or other than all the suspended, forget about bacteria, virus, and this one. This way, your reflected energy from the water column is a function of backscatter by absorption from backscatter, which is a function of pure water backscatter plus the deep phytoplankton by the water plus phytoplankton plus gelb stock plus water plus absorption. Same with A also. Okay, these luckily, whatever the downward, this column, okay, this column is called the additive term. Additive term. That means the total backscattering is a composition or a mixture of, or is a function of vectorially. That means if I know the individual component, I can simply average it and make it total. That is the lucky Narayana operation. Okay? Pure water backscatter to the suspended particles, backscatter for the organic plus inorganic together, or backscatter from the bottom reflectance. This bottom is very shallow and is known like sandy or rocky. Light also emerges from that. No? All this individually measure, add it, then I get the total backscatter. Okay? If I know the total, I know the pure water. If I can able to measure the individual backscattering contributed by the so-called material present, then also I can measure it. But this is very complicated. But A absorption is also a pure water absorption. Absorption due to the phytoplankton, absorption to the gelb stock, absorption of other material is very easy. Why? If there is no sedum, okay, what is my phytoplankton absorption? Directly proportional to the presence of the phytoplankton or the chlorophyll. If I measure the chlorophyll, if other species is, then total chlorophyll is known, total absorption coefficient is known, R is known, R is equal to B by A. I am measuring the radiometer or photometer which is given by NA, total reflectance at the sea surface, correct? Just below the water column of 0.5 meter, just above the water column is water column, just above the water column, as much as in the avoiding the atmospheric line, I measure the reflectance, correct? This reflectance is a function of dB by A by some constant. A is known because simultaneously I measure the chlorophyll, then absorption I measure, D can be measured. Individually possible because there are vectorially additive terms. All individuals add all this one, you will get the total. Okay, that means what? If a marine ecologist, expertise, measure the phytoplankton species or functions of all, measure the specific absorption of that so-called phytoplankton species, right? You have phytoplankton, number of phytoplankton, peridotite, all that is there, no? Diatom, what is it? So many, whatever you name, there are n number of phytoplankton, thousands of phytoplankton. Whatever is possible, you segregate, measure the concentration of that species, and say for example, we have to measure the diatom, we have to measure the other duplex, or peridotite or peridine or whatever we call it, segregate, measure its concentration, come to the lab, measure the specific absorption of that species or of that type. Okay, add all these, I will get the total absorption of the phytoplankton. That's why you have a powerful underwater radiometer. Also, you have UV spectrophotometer. which can measure this. All these species are the different phytoplankton height absorption coefficient individually. But the lucky or the greatness is, if I built up the specific absorption of this particular species or the particular phytoplankton, I need not measure at the time. What I mean, he had an absorption coefficient, is measured to only Kiran. Okay, if I know this, only the strength of the Kiran and the strength of the other multiplied by the already in the available lab or the built up or the spectral signature or I only measured earlier, that multiplied by I can get the total absorption of Kiran. Like that, all individuals A plus B, specific, what we call this specific absorption coefficient of that phytoplankton type. That you have to build up in the lab. Go to the area, do the phytoplankton analysis, measure the what are the major dominant species, build up your specific absorption, keep it in your library, then measure simply concentration and add it, total you get the absorption. Or reverse way, every time it is difficult. Okay, I just come, like your people told me, I just measured all the phytoplankton, see the electron what is that electron microscope. I have different species. Okay, then I also know by the different species volume of cells is known. That means concentration is known. Multiplied by already available specific absorption of that one, add all this one multiplied by that. Concentration of that phytoplankton species multiplied by the specific absorption of that species gives the total absorption. Like that I will have 2, 3, add I will get the absorption. Once having the absorption, I also have the reflectance at the surface, which is a function of a constant G multiplied by B by A. A is known, then calculate the B. That is the fundamental optics, this is what is being defined. R is equal, first term, Anis will tell, that is LW by ED, water leaving radiancy by the diffusive irradiance. Okay. R directly proportional to B by A. Now what is the relation between the LW and A or LW and R, you will explain. Either way it will measure. If you measure the reflectance from LW or by knowing the LW and R, because from remote sensing, ED is known, LW is water leaving energy or water leaving radiance or light energy from the water column. How I told, I know at the top of the atmosphere, multiplied by the simple atmospheric transmittance, I know the light available at the sea surface. By knowing the diffusive attenuation coefficient or the attenuation coefficient of the water column, and I know the back, whatever the energy reflected back is what total sensor measured minus the atmospheric column contribution is the energy emerged from the water column. That, from that water leaving radiance is nothing but the LW. Downwelling irradiance is known by atmospheric path length is calculation. If I know the transparency of the total transparency of the atmosphere multiplied by that, I will get the ED at the surface. ED is known, LW is known, LW is known, ED is known, R from remote sensing. ED is known, LW is known, R is known. By having R, B by A, if I know the A, I can calculate the B. That is where the remote sensing. What basically you have to know? You have to build up the absorption coefficients. Okay? And the absorption coefficient depends upon what we discussed. You build up a spectral library of absorption coefficient for different species of your area, keep it in a library from remote sensing, simply calculate. All the remote sensing equations you will get. Okay? We'll stop here. So now what is to be transferred to you? This fellow. And is where I
leave it at
equal RS here?
Yes, sir.
Huh?
Good.
Yes.
Shall I copy there?
Yeah.
Second one is that. Right. Okay. Marine optics lecture also. No? Lying. I have a lecture also, you can read it. This I not. These, you have all that overseas is the aeronautics lectures. These is not there. Okay, leave it. Okay, I think this lecture note is enough. Yeah, this is what we discussed. Devotion optics lecture. Yeah, you take this PowerPoint, this light what we discussed, penetration of light, and total ocean optics lecture is available. Those who are familiar with a little bit mathematics, you can go through this. Whatever we discuss in this, it is there in the lecture. Any doubts, any questions? So the what of that absorption coefficient, reflectance, is operationally derived products are available from most of the ocean color sensors. I think there are a number of color sensors are available. From NCAI's data library or NCAI's Earth station, you have OCM2, you have MODIS, you also have the VIRS, visible infrared remote, visible infrared zoom, that is called. Number of spectral bands versus 8 spectral bands of OCM. Physically, you have OCM2 data today, you have MODIS data, and you have VIRS level 1B data. Who are familiar processing of level 1B on your own using any CDOS package, you can experiment. Otherwise, from NCAI's, you can have chlorophyll, also reflectance, also absorption at different wavelengths, also available. Go to your lab, measure the species, and correlate and tell this absorption is because of thickness. This all data is available. Any questions? No.
So if you want to use the search disk in open coastal waters or open oceans, so what is the effect of currents?
We had some weight on the ground.
Okay, but
See, radiometer you cannot weight any weight. In dead weight you had about 10-15 kgs or 5-10 kgs of different dead weight. Really what we had was,
not able to go vertical.
no, you had as much of weight because SETI disk is this. Adding weight under the down is no problem. Have a length of the chain, just 2 meters or just 50 centimeters above with this SETI head. Below that you add the dead weight. That's what we will do for any radiometers also. Because what you are expecting is where the SECI disk is disappeared. Correct? See, that data is only for marine ecologists for ages from so-called Charles Darwin to the 1985 until the Caesar CS is launched, 1978 rather. Okay, until that only marine optics for ecology is only SECI disk. As we discussed, SECI disk speaks a lot because you know the F, you know the K, you know the C. By knowing the SECI disk there, if you have 8.7 to 6 in general, okay, then you can estimate the attenuation of loss or the K. Once you know the K, then this is all the story of marine. That's why SECI disk is very powerful, but unfortunately, we didn't have much measurement, we didn't take care much. And SECI disk is not a part of the routine hydrographic measurement. Unless ecologist goes to the field or optics goes, you would measure the SECI. Next lecture is Arizona, no? Or tea break.